All right. So welcome everyone. For those who are new, this is our Geo-Regional Africa group under Cohere for AI. So if you haven't joined the Cohere for AI Discord, I suggest you do. So today our guest is Dr. Adaku Uchendu. I'm very sorry if I tortured your name. She's an AI researcher at MIT. She earned her PhD in information sciences and technology at the Pennsylvania State University, and she earned her BS in math with a minor in statistics at the University of Maryland. So I will let the other things to be explained by her because it's a lot. She have achieved a lot of things. So yeah, you can share your screen and start.
Thank you so much. For if there's any question, please let me know because I can't see the participants while I'm the audience while I'm presenting. So the title of this talk is Attribution and Obfuscation of Deepfake Text Authorship. Henoch has already introduced me, so just a little bit about me. Like I got my PhD at Penn State and I got my bachelor's in math at University of Maryland, Baltimore County. This is the outline for the talk today. I will introduce the talk, and we'll talk about the two problems, deepfake authorship attribution and deepfake authorship obfuscation. We'll discuss the open problems, and we can go to Q&A. So large language models, I'm sure we have all heard about this, and it's a very popular term now. And I'm not going to go into too deep into this, but like this is like the user interface for ChatGPT, which I'm going to assume that everyone knows. So I call this text that large language models generate a deepfake text, which means deep learning based synthetically generated text. In this field of large language models, especially with like studying their texts, given that it's still a new field, different researchers call it different terms like deepfake text, neural text, machine generated text, AI generated text. Like you can see all of it around the circle. So the question can be like, why do I call it deepfake text when there are so many? Honestly, I feel like deepfake text just has more. Like when you say deepfake text, people pay more attention than when you say machine generated text. There's no really any deep reasoning why I chose that. And this is just an example of like how you can generate a text. So I give it a prompt, generate an unhinged story about Beyonce. And, you know, I'm not going to dwell on this slide for too long, but the story is a bit unhinged. So now I will like the audience participation here. So there are two pieces of text here, A and B, and the choices are both are human written, both are human machine or LLM generated, and either one of them is AI generated, and which one is AI generated. Does anyone want to try?
I'll go first and say A.
A is
Diana say B.
Okay. Actually, did someone want to say something? Okay.
Two people said both.
Two people say both. Okay. This is the first time I've done it, and people actually got it. Both of them are AI generated. I use two different prompts with ChatGPT. So for the first one, I just said, generate me something about like Game of Thrones, like a summary. And then the other, for B, I asked it to generate me the same thing, but like I'm a 12-year-old. And people tend to choose B. But this is just like one of the amazing things that we get with ChatGPT that we didn't have with like older language models. So, needless to say, we are in the age of ChatGPT. We look at other popular social media, um, like Instagram and Spotify. Like it took like 75 days for Instagram to reach 1 million users, 150 days for Spotify to hit 1 million users, but then it took ChatGPT only 5 days. So, you know, everybody knows ChatGPT now, everybody's mother, everybody's grandmother. And people use it to do different things like generate code, write their emails. It's just in everything that we do now. And we can see the exponential growth of large language models. So like they started off with smaller language models at the time, which wasn't small. They were known as they were pretty large at the time. Like in 2018, that's when GPT-1 and BERT came out, and you can see it at the bottom. And then fast forward to 2023, we have like um, Palm 2, Claude, and you have like several billion parameters. And these people are not just increasing the model size blindly. They're doing so because they can generate better quality text as you increase the context window size and the hyperparameters. Another place we've seen a boom is in Hugging Face. So Hugging Face, like if you go to the text generation part, it's like almost 100,000 um, language models, and these are not like unique models. These are like different models fine-tuned by people, and this is as of yesterday. There's 93,000. But even though these models are so impressive and we love to use them to write our emails, our papers, and do our homework, they have issues. One of them being toxicity. So when prompted, there's this thing called like persona-based prompting. So when prompted, like someone who might be perceived as a toxic person, it's able to generate toxic content to go with that persona. So like, as you can imagine, if you use Adolf Hitler as your persona, it's going to generate like a lot of toxic content, which many people don't want in their generations. You don't want this language model to be able to spew the hate and toxicity that unfortunately people spew on social media. Second is bias. So there's like a lot of bias towards different like groups of people. One of them being Muslim, because the wealth of content on the internet about Muslims are very negative, and so these models essentially learn these negative connotations and are able to generate pretty violent content when prompted with such groups. Another thing is memorization. So when you train your model with massive amounts of data, sometimes the model memorizes some of these uh, content, and this can include like personally identifiable information. So which is not very safe. And then another one is plagiarism, where these models can generate verbatim from their training set, paraphrase, or like do um, an idea plagiarism. And what makes this stuff like very like bad is that like it generates content like it's a new concept without citing the reference. Another one is disinformation, like which is the one of the scariest things that these models can be used for. They can be used to generate specific types of disinformation, and several papers have found that some of this disinformation that it generates is actually very believable when they do like a human evaluation on it. Like humans believe this LLM generated disinformation. So now the question here is like, how can we mitigate these issues? And no, we cannot break our computers like Patrick is doing, because all these models are like kind of imbued in our society at this point. So some typical ways that people have attempted to solve this issue is like they go to specific issues like the misinformation, and then they develop like metrics to first of all detect it, and then maybe they can propose some techniques to improve it. So like, for instance, in order to avoid, to make it not generate disinformation, or mitigate the rate of disinformation it generates, people put all these alignment tuning stuff, which sometimes people can jailbreak, but you can also like you can jailbreak to make sure that the model cannot be jailbreaked so easily. So using all these metrics like truthfulness, safety, fairness, robustness, people can develop these metrics and evaluation techniques. But how I choose to mitigate these limitations was just to distinguish LLM or deepfake text from human written text. Just a side note, this problem is very similar to the Turing test problem that was developed by Alan Turing in the 1950s. And the way this test goes is it's a way to test how human-like a machine, or in this case, an LLM is. So if this is typically used in like chatbot competition. So like if a chatbot shows like intelligent behavior that is like typically attributed to a human, then you would consider it a human, and so it has passed the Turing test. Now, obviously, we do not want this to pass the Turing test. So what we do is we automate it, and by automating it, we create the reverse Turing test. In the Turing test, the human is the judge. For the reverse Turing test, a computer algorithm is the judge. So we automate the process. And now we're going to go into the deepfake authorship attribution. So traditional authorship attribution has been well studied. This is a case where you have several humans who wrote a text, and that can be like, um, can we decide if it was Shakespeare or some other person who wrote this article or this story? But for deepfake authorship attribution, the goal is to distinguish several LLM authors from a human. So all human authors are just given the label human. You can also use separate humans as well. You can, use like maybe Washington Post versus New York Times versus Llama versus GPT-4. But for simplicity, I used one label for human. The landscape of detecting deepfake text comprises of pre-hoc and post-hoc detection now. For pre-hoc, people use watermark-based models. So in a utopian society, we can hope that these creators of LLMs can uh, put watermarks, which would easily make these models detectable. But so far, that has not worked out. So since we are living in the real world, we have to develop like post hoc techniques, and this include like supervised, unsupervised, and also improving humans' ability to detect or distinguish deepfake text from human written text. So I defined several categories for this. This is the taxonomy. We have stylometric attribution, which is looking at the linguistic styles of the written text. And there is deep learning based attribution, which uses different pre-trained embeddings to um, represents the text before classification. And then statistical attribution is looking at things like what is the probability distribution of the text. And then hybrid distribution has to do with like combining um, two or more of the techniques I described. And then human-based approaches include improving humans' ability to detect this text on their own, either with training or without training. So now we're going to stylometric attribution. Does anyone have any questions before I go ahead? Okay. So stylometric attribution, we define stylometry as a statistical analysis of variations in literary style. So we are looking at different linguistic patterns that signify the signature or style of a writer. In forensic analysis, they use a stylometry heavily. They look at the writing of the text. So how did this person write their R? They look at the construction of the sentence and all these things. But we cannot use this approach for the machine learning model. So we use the approaches that can transfer well to online written text. So we studied three different problems. This is the problem one is the popular authorship verification problem, where you look at two texts and then you ask if it's written by the same author or not. So this is a binary problem. The second one is another binary problem, which is the proper Turing test. So is this text written by a human or an LLM? And then the third problem is the authorship attribution one. This is multi-class. So now we know that this is written by an LLM, but which LLM? Is it ChatGPT? Is it Llama 3? Is it GPT-4? Yeah. So this is the technique that we used. We combined three different linguistic features. So LIWC, which stands for Linguistic Inquiry and Word Count, Readability Score, and Entropy. And then we used a classical machine learning model like Random Forest. So for the readability score, you get like a score depending on how easy or hard the text is to read. And very easy means that the grade level of the author is like the 5th grade, and this goes up to post-college. Then the linguistic inquiry and word count is a psycholinguistic dictionary. So you you count stuff like, so like a feature friends, they would count words like pal, buddy, coworker, and other kinds of synonyms that represent friends. And then for entropy, we calculate the measure of uncertainty. That's the definition of entropy. Now, there are different ways to calculate entropy, and some of them can be intractable. So we use this simplistic approach where we just calculated the number of unique characters. And here are the results. So we see that Random Forest achieved the highest performance, outperforming several deep learning based models like embeddings, RNN, stack CNN. And so the summary of this attribution technique is that linguistic features are able to capture an author's writing style. And I should say that this work was published in 2020. So since then, language models have improved significantly. And linguistic features are explainable, but feature extraction and engineering can be expensive. And we agreed that creation of more sophisticated models, language models, will increase the difficulty of the problem. Like if you see in this plot, which is a PCA plot of these linguistic features, we see that even though they are like stacked on top of each other, you can still see distinct clusters. These are clusters that might not be so distinct when comparing the newer LLMs like Llama 3 and Claude and all these other models. So any question before we move to the next one? Okay, so now I'll talk about the deep learning based attribution that I tried. it was a transformer. There are different deep learning based models: glove, energy based, and transformer based. The most popular is transformer based, which I used. And this is the typical structure. You get the article, you pass it through your transformer layer, you get the pulled output, pass it through the dropout layer, and get the regularized weights that you put in your linear layer, and then use it for classification. And this is the benchmark data set that we proposed. It has 20 authors, so 19 language models and one human. And we looked at two problems here. The Turing test one, which is the binary classification where the authors are human and machine, and the multi-class one where the authors are several K number of LLMs versus human. So for the Turing test task, which is the binary classification, we looked at human versus each of them, creating 19 subtasks, and we compared different state-of-the-art detectors: Grover detector, GPT-2 detector, Glitter, BERT, and Roberta. And we find that BERT achieved the highest performance. And then for multi-class setting, Roberta achieved the highest performance, just slightly outperforming BERT. And then we created like a benchmark of multilingual data, a multilingual data set of these LLM generated text with 11 languages and 8 different generators. And we find that the deep learning based models are also performing quite well in this task. So in summary, deep learning based attribution, we need sufficiently sized data to perform well, and fine-tuning the neural networks with a decent data will improve the performance. But data is not always going to be sufficient, and so that's why statistical based approaches are considered. So we propose a statistical based attribution called GPT-Who, which uses psycholinguistic theories like uniform information density to calculate the UID of the text, the surprisal of the text, and classify the text. And we find that GPT-Who leverages psycholinguistically motivated representation and is able to distinguish very similar text that are written by different authors. And so we find for out of distribution performance, these scores are F1 scores, that GPT-Who significantly outperforms these state-of-the-art models like Glitter and DetectGPT. Next, we propose hybrid attribution. So, like I said before, hybrid attribution is like a mixture of different of either stylometric, statistical, deep learning based. The more popular technique is the deep learning based and statistical combination. So we can have stylometric and statistical, stylometric and deep learning, and statistical and deep learning, which is what we propose. So combining transformer-based models and topological data analysis. So why did we use topological data analysis? Because it's a short study of shapes and structures, and the process of data analysis makes it robust to noise and robust to out of distribution data set, which can be considered as a kind of noise. So the TDA techniques that we use is persistent homology. And persistent homology is a method for computing topological features of data using different spatial resolutions, which I will explain later. And these features are typically represented in a persistence diagram. So they're different. So the TDA technique aims to get the features in different holes and holes in different dimensions. So the zero dimension is called connected components. And so imagine the yellow circle is a point. I know that's quite large for a point, but imagine it's a point. And this is this is a cube. Yeah. So this is a cube, and then this is a sphere. We find that because they are all it's a connected point, so they all have one connected component, and then tunnels is the hole in the one dimension, which I'm not going to get into because it can get complicated. So this is an example of how we use persistent homology to get features. So how it works is that each point is enclosed in a circle, and you just keep increasing the radius. So when the 2 points touch, one point has died. So the features are called deaths and births. So when it dies, you record the time when it died, and this is what is recorded on the right here. And just a reiteration of how that works. So this is the points at radius 0.3 and radius 0.5. They've joined together, and then you draw a line when it gets connected, when the circles touch, and radius 0.7. So you keep going until all the stuff are connected, and then you record those points. So the proposed model is like just including a topological layer in transformer-based models like Roberta. We chose Roberta because it's a pretty good baseline. It has about 20,000 more vocabulary size than BERT. And this is the proposed approach. So you have the vanilla transformer-based model structure. We take the regularized weight and we reshape it to a 2D matrix because the topological layer requires a 2D input, requires an input greater than 1D. So it can be 2D, can be 3D, but I use the 2D. I got the topological features, concatenated them, and then used them for classification. And then we evaluated the model on an imbalanced noisy data set. As you can see, this is like all the human labels, and these are the uh, deepfake text. So as you can see, like it's like so imbalanced. And we see that Roberta is achieving a pretty good F1 score, but we can see that top former, which is the name of the TDA based model that we propose, improves by almost 4%. So top former outperforms by a larger margin. And summary is that it's able to comparably perform with deep learning models. Sometimes it outperforms, like we saw there, and it potentially could be more interpretable than deep learning models, especially when combined with stylometric attribution techniques. So the key finding among these automatic detectors is that like hybrid and deep learning based models perform about the same in terms of like accuracy. So now we'll look at human based evaluation. Any questions? No questions. Um, so we look at without training. So we did two studies. One, given a text, is it written by machine or not? That's what we asked the humans using Amazon Mechanical Turk. And study two, given two texts, A and B, one is human written and one is machine generated. Which one is machine generated? So we find that on average, humans perform just at random guess, slightly above random guess. And for study two, um, for actually study one, while I asked, is this a machine or not? What the humans did not know is actually I only gave them machine generated text. And then for and we try with training. In this one, we look at can collaboration improve performance. So we look at individual versus collaboration, and we also looked at what types of reasoning and explanations are useful indicators for defect text detection. And so this is what the user face look like. So you have three paragraph text. So we had three paragraph news articles where one of the paragraphs was replaced by an AI generated one, and we asked them to choose which paragraph is deepfake and explain why they believe it's deepfake. So this is the data generation process. So we collect human written articles, and we only collect the ones that had at least three paragraphs. And if we had more, we just took out from the fourth paragraph. And then if and then we randomly replace the paragraphs. So if paragraph one is to be replaced, we use the title as the prompt, and we use GPT-2 for generation here. If paragraph two is to be replaced, we use paragraph one as the prompt to generate the defect. As if paragraph three is to be replaced, we use paragraph two to generate. We use paragraph two as the prompt. And then we looked at two different types of participants, like experts and non-experts. Non-experts being people who did not study English or related programs in college, at least. And we gave the non-experts training, an example-based training where you give them an opportunity to get acquainted with what AI-generated paragraphs look like versus human-written paragraphs. And these are the results. So for individually, the non-experts achieved 45% on average accuracy, and with collaboration they improved to 51%. However, for the experts, which are people who have like an English degree or related or a degree in a related program, they achieve 56% individually, and then collaboratively they improve to 69%. And the baseline here is 33% because it's one out of three paragraphs. And I also prompted ChatGPT to perform the task, and it achieved only 38%, suggesting that this problem is non-trivial, and the improvements that we see here are also statistically significant, more so for the experts than for the non-experts. So summary here is that collaboration can improve performance. And for the non-experts, we use synchronous collaboration. We use asynchronous collaboration using Amazon Mechanical Turk, because it would have been a lot more difficult to make to do this synchronously. But then for the non-experts, we recruited participants using Upwork, and so we're able to have synchronous collaboration, which we can see improves performance. But we cannot make a strong conclusion here because we use different types of expertise for both. And experts are able to distinguish between AI-generated paragraphs and human-written ones. So now we'll go into the authorship obfuscation side of things. Any questions? Okay. So deepfake authorship obfuscation. So authorship obfuscation has been studied in the human authorship attribution problem. So it's the process of masking an author's like writing a signature to conceal their identity. And this can be used for privacy reasons, like say a famous journalist whose writing style should be well known, wants to write a piece that might cause a lot of problems. They can use authorship obfuscation things to mask their writing style. And so this includes like you get a text, you have an authorship attribution model which accurately attributes the author as author A, and then you pass this through an authorship obfuscator, and it now misclassifies. For the sake of the deepfake authorship attribution, we are interested in like changing the writing style while preserving the semantics, such that like a human can be attributed as some LLM, and llama is no longer um, uh, accurately attributed as llama, but some other LLM, etc. So why does this matter? It matters because say you have a piece of text. Viola Davis did an amazing job in Woman King. I think she did. I think you should watch it if you have a chance. And you pass it through an authorship obfuscator, and then you get Viola Davis did an outstanding job in the Woman Prince. We find that you can change the authorship of the written text. So it doesn't serve well that we have all these different authorship attribution techniques that can help us in different types of scenarios when there's enough data, when there's not enough data. But then they are not robust to adversarial perturbations like authorship obfuscation techniques. So we define the taxonomy for these techniques based on what people have so far. We have the lexical obfuscation. So we have the difference are stylometric and statistical. Under stylometric, we have lexical, syntactic, morphological, and orthographic. And for lexical, this can be defined as word choice, a syntactic word order, and morphological word form. And then orthographic can be defined as the way we write, but we can just distill it down to punctuations for this task. So you can see an example here. I got 99 problems, but you won't be one. So for word choice, you can change got to have. So this has to do with lexical changes. And for word form, you can change numerically written 99 to spelling of 99. And for word order, you can change the structure of the written text. So I got 99 problems, so I have issues 99 to be exact. And punctuation, you can just change like maybe the comma to a semicolon or whatever is necessary. And so here are some examples of stylometric obfuscation. So the homoglyph attack is a pretty impressive attack where you just change the Unicode of letters and it looks the same. So like, I changed, if I were to escape, you see that the hello that has been changed would be underlined, because while we can see it on with our naked eyes, like the editors, the writing editors can see, like Grammarly can see that that it's not the same. And these technique can actually, while imperceptible to human eyes, can cause your models to misclassify at an alarming rate. And there's the upper or lower flip where you just randomly flip the case of a character. Misspellings attack. You can look at these list of common misspellings in the English language, and you can use that to replace words that humans will catch, but like will cause your models to misclassify. White space and different types of attack techniques. And then there's the statistical obfuscation, which is a little bit more complex. But what it does is that you are taking the generation and changing the way that the generator generates the text. So instead of making the generator generate like highly probable text, you can make it you can change the probability distribution or of the text. So by making it uh, select improbable generations, but at a different pattern. So now we look at the authorship obfuscation, like in the multilingual machine generated benchmark data set, which I talked about, multitude. So we looked at three different obfuscation techniques using back translation, where you can translate from English to Spanish back to English, and that changes the structure of the text, misattributing the author, and paraphrasing, which is the most popular obfuscation technique now, and different types of attack. And we evaluated these obfuscated texts with different detectors, fine-tuned, pre-trained, and statistical. And here are the examples of here's the techniques that we used. Using like multilingual models for back translation, and using like Pegasus, Dipper. Dipper is the most popular one for paraphrasing now, and using different like attack techniques. And we find that these models, like on average, actually are able to reduce the are able to achieve like high success rates, um, at least for GPT-0 bypasser and homoglove attack. But for some other models, they don't achieve very high success rates. So in summary, the authorship obfuscation techniques for deepfake text, actually, we find that hybrid attribution, this is from the survey, we find that hybrid attribution techniques are more robust, even though they are able to achieve similar performance as deep learning. They are more robust, and deep learning attribution is the least robust model. So now we discuss the open problems. In conclusion, we are in the age of deepfake text, and we are moving from a scenario where LLMs and human writing distributions are separate, to be where they are very similar, making this detection task non-trivial. And we are in an arms race between deepfakes and their detectors. And there are several open problems here. We need novel training human-based evaluation techniques. As of right now, humans are not very good at distinguishing deepfake text from human written text, and we need more explainable models that are able to withstand adversarial perturbations. Because right now, the explainable models tend to not be very robust. And then we need to also look at like harder constraints, like for instance, when there are several human labels, because right now most of the techniques, there's only one human label. So this is the realistic future of deepfake text detection. We need to study the generators, so the LLMs, their detectors, and different obfuscation techniques together, so that we can build models that can withstand newer LLMs. So questions? Thank you.
Wonderful. It was amazing. Yeah. So everyone, open your mics and you can ask. If you can't, you can drop them in the chat and I can ask them for you. So maybe until then, I will start with my questions. So these LLMs are like as you know, they are increasing in their reasoning abilities and like the common sense knowledge, as we have seen in the last few months or like a year. And like they are also increasing their context window, where they can process the inputs like very much. So will that, I mean, now they can process a whole book, you know. So does that make the whole problem here harder, or like how is that going to be?
Oh, it definitely makes it harder. Like, um, in this stuff, like I studied, um, first of all, like it's the detection problem is like very dependent on when there's data, and it gets harder and harder to generate these benchmarks like with newer models. So like I don't think there are any benchmarks that uses like those large context windows. So like you create your detector based on the current data, and then somebody generates something with those models with large context windows. Your model won't perform so well. So that definitely makes it much harder. And then not to even include persona-based prompting. So like you can see that there is a in the example that I showed in the beginning, this like it looks like two different people wrote it, but it was ChatGPT that wrote it. So that also makes this like really hard.
Okay, perfect. Anyone with questions?
Hi. So, are there any tools out there such that we can differentiate between the LLM generated text and the human ones?
Yeah, there's actually this is since ChatGPT came out, many startups have come out and proposed their own API based techniques. So there's actually a lot there. I think the most popular one is GPT-0. Uh,
Mhm.
yeah, but there's a lot. Yeah.
Okay, thanks.
Okay. You think like synthetic data could reduce the toxicity when training new LLMs?
You do you mean sorry, what was the question again?
Um, do you think like synthetic data could reduce the toxicity when training new LLMs?
Synthetic data with toxicity.
Yeah, do you think like it can reduce the toxicity? Because
Oh,
you
it can
see
reduce
like
toxicity.
yeah.
Okay. Oh yeah. I don't know if it can, but people have done research on using synthetically generated data with these LLMs to um, train their model, and what they find is that it actually um, reduces the linguistic diversity and quality of generations. So some of the reasons why people don't want to generate, people don't want to put some of these safeguards on their LLMs is because it actually reduces the quality of generations. So I'm not sure if it will reduce toxicity, but I know it will reduce the quality of the generation. I don't know if I answered your question.
Yeah. Thank you. Thank you.
Okay.
Yeah, maybe I also have one question. So you mentioned the human experts. So like, how can someone leverage the human experts in the authorship attribution and like style detections to improve the deep learning models?
You mean like human in the loop process for authorship attribution?
Yeah.
Yeah, I mean for people have proposed some human in the loop techniques. The issue with the issue behind that is that one is like it's very it is it needs the model needs to be interpretable, and not just interpretable, it needs to be intuitively interpretable. And some of the models that the reason why people don't typically do it because like explainability in I think NLP is still kind of like an open problem. So but they do have models like glitter is a human in the loop problem in human in the loop detector where they highlight the most probable words in green and the next least probable words in yellow, and then the next one in red, and then the next one in purple. And the idea here is that like human written um, text will have more least probable colored words, and AI generated text will have more highly probable words. So it will be very green. But this was made in 2019, and since then ChatGPT came out, and it just looks like human written now using that model.
Yeah. So maybe in the long run, do you think this problem, this question will exist in the near future? Because it's a dead end for me. Like they are becoming more aligned. Like how do you see like the deepfake research going in the next like 5-10 years, let's say? Is it even possible to detect?
Yeah, I think in the future, probably watermarking would be the what would make this problem not become as crazy as it could be. So if like these creators of LLMs are forced by I don't know Congress or whoever to uh, put watermark techniques on their LLMs, then it will make authorship attribution like still possible. But if not, I honestly don't know.
I see. Maybe like I have one last fun question. Like while working or and looking at all this model generated content, do you like developed a technique like to identify some linguistic patterns, like quirks, to identify like, oh, this thing is generated by this model? Like, have you developed something like that just personally?
I mean, yeah, but like, I want to say like my, because I started working on this stuff like in, I'd say 2019, 2020. So my ideas of distinguishing them are very much based on the models that came before ChatGPT. So I don't know. I don't think that will transfer very well in ChatGPT. But I've used ChatGPT quite often, and when I like, let's say I use it, I write something and I want it to edit and all that stuff, or I want it to generate something from scratch. It's a bit obnoxious, I feel like it generates things in a way that typical humans would just not write. So that's kind of how I will separate for ChatGPT. But my working with all these generators, I find that they tend to be more verbose than humans in general. So that's one way I know like they would probably have more run-on sentences than humans. However, they have less grammar issues than human written text. Yeah.
Awesome. So we are running out of time. So if there's like 1 to 2 questions, I can ask them for you.
Somebody says watermark seems not a good idea.
Um, I don't see any questions, so I don't know about the near future detecting deepfakes in generators, to be honest. I mean, Adaku's paper is going to be a big input for these big companies, to make them more aligned to human-generated ones. They will, I think, reverse use it, and it's going to be a big task with models being trained on a vast amount of data and a lot going on with the architecture itself as well. So let's all say good luck for Adaku in fighting and combating this thing. It's a big challenge, and we are rooting on you.
Thank you.
All right. So other than that, yeah, I wanna say thank you. You just became our guest in a short notice, and please be active in our community. I would like to see you again in Cohere for AI events.
For sure.
Yeah, and all of you who attended, thank you so much. And I will see you in the next, in the coming 2 weeks, I think 2 weeks from now, with another guest. And until then, bye everybody.